Hello Chem 152 students. You guys are beautiful. Today we are going to be covering radioactive decay and nuclear bombardment, which is essentially some major types of nuclear equations. Now the first one is that we're going to cover is alpha decay. This is where a nuclei, an unstable nuclei, or an unstable nucleus of an atom, it becomes more stable by releasing an alpha particle. This is essentially the same thing as a helium nucleus, but without the electrons attached or orbiting around it. So I'm going to represent this. It could be represented as He or alpha. I'm only going to represent alpha particles with an alpha symbol. Two things to make note of is the upper leftmost number, which would be the mass numbers, and then the bottom left number, which would be the atomic number. For nuclear equations, we are going to be focusing on balancing the sum of the mass numbers on both sides of an arrow and balancing the sum of the atomic numbers on both sides of the arrow. Let's take an example of doing this with polonium 210 breaking apart into an alpha particle and some other element. Well, let's just look at the mass number. In this case, for the K, we only see one component on the left side, so pretty simple to sum up those mass numbers. That's just going to be 210 thanks to polonium, and the atomic number is going to be 84. Now, the mass number for the right side, it is going to have to add up to 210. Well, we already have a mass number of 4 thanks to our alpha particle. Therefore, what plus 4 would equal 210? Well, 206. So this guy is going to have a mass number of 206. The mass number for an element can range depending on its isotope. It is actually the atomic number and only the atomic number which tells us the identity of the particular type of element. So let's solve for the missing atomic number. Well, the right side, the sum of these lower two numbers are going to have to add up to 84, and we already have 2 thanks to the alpha particle. So what plus 2 equals 84? Well, 82. Therefore, our atomic number is 82. Now, if we go to a periodic table, we can see that the element with an atomic number of 82 is going to be lead. So now we know the identity of our missing particle. We can just fill that in as lead or PEB. Therefore, we have now solved our first nuclear equation, where we essentially balance the sum of the mass numbers on both sides and the sum of the atomic numbers on both sides. The mass number, which would tell us the particular isotope of the element we're working with, the atomic number, which would tell us the particular element we are working with. Now, we also have another situation of decay, which is called beta decay. This is simply a nuclei that needs to release a beta particle from inside the nucleus in order to become more stable. Now, this is effectively that beta particle is essentially a very high energy electron. Therefore, it could be represented as an E or a lowercase beta. Now, since I want to distinguish between electrons that are normally orbiting an atom versus one that was simply formed from inside the nucleus through perhaps the breakdown of a neutron into a proton and a beta particle, I'm going to represent these electrons with a beta instead of an E. But you could use either and still be correct. An example of beta decay would be that of iodine 131. In this case, our mass number on the left side adds up to 131. And on the right side, well, our beta particle has a mass number of 0. Therefore, what plus 0 equals 131? Well, 131. And the atomic number on the left side of the equation is going to be 53. Now, we need to come up with a number that when you add -1 to it, it becomes 53. Or effectively, what plus -1 equals 53? Well, 54 plus -1 would equal 53. Therefore, our missing number is 54. Now, if we go to our periodic table, we see that 54 represents the element xenon. So, cool, a noble gas. Therefore, we can fill in the identity of our unknown as xenon. And there we go. Cool. So that would be an example of beta decay where an unstable nuclei released a beta particle. Now, there is another version of decay. This one's pretty fun. This is a gamma decay. Now, a gamma particle is really just released energy. Essentially, a nuclei might be in a high energy excited state, and in order to become more stable, it needs to release that excess energy. And one way it can do it through radioactivity is through the release of a gamma particle. Gamma particles have no mass number and no atomic number. Therefore, they are just pure energy. So they're very easy to work with. In the case of an excited element, in order to understand whether an element is excited or not, you will see this asterisk here. So if, say, I didn't show you the gamma particle, but you saw this asterisk, you would know that one of these unknown components would be a gamma particle. Now then, to basically solve for this, let's say the mass number is 60 on the left side of the equation. Well, our gamma particle has a mass number of 0. Therefore, 1 plus 0 equals 60? Yep, 60. In the case of our atomic number, it's going to be the same exact math. Our excited cobalt element has an atomic number of 27. Well, the gamma particle has an atomic number of 0. Therefore, 0 plus 27 gives us 27. And we don't need to go to the periodic table because every particular element will always have its own unique atomic number. So, if the left side of the equation tells us cobalt has an atomic number of 27, then the right side of the equation would be cobalt as well. So, cool. Now, this another version of decay is similar to beta decay, where a high energy electron was released, but there are situations where you might release a high energy positron. A positron is simply an anti-electron. It has the same mass as an electron, but it is positively charged as opposed to negatively charged. And the way I'm going to represent this is simply with a beta that has a charge number of +1 instead of -1. Now, an example of beta emission where a positron was emitted, well, we can do it like so. The left side of the equation only has oxygen to worry about, therefore we only have a mass number of 15, and the products must add up to 15. Well, our beta particle has a mass number of 0, therefore 1 plus 0 equals 15? Yep, 15. And for the atomic number, well, oxygen has an atomic number of 8. Now, our beta particle, our positron or beta positive particle, it has a atomic number of +1. Technically, that's actually the charge, but for nuclear equations, we can consider charge number and atomic number pretty similar for addition. Now then, what plus +1 would give us 8? Well, 7 plus 1 would give us 8. Therefore, the missing atomic number for unknown nuclei is going to be 7. Now then, what has an atomic number of 7? Well, that would be nitrogen. Therefore, we can fill that bad boy in like so. Just nitrogen. There we go. That is a balanced equation. That is a balanced beta positive / positron emission decay equation. Now then, another example of radioactive radioactive nuclear equations could actually be an electron capture. This is essentially when a nuclei, uh, this essentially is when a nuclei absorbs an electron, converting a nuclear proton into a neutron, or effectively one of the inner shell electrons of that nuclei, it collides with the nucleus and essentially fuses with a proton, ergo forming a neutron. Now, since the source of this electron is from those that were orbiting the nucleus, and this wasn't something that was formed out of the nucleus, I'm not going to represent this with a beta, but only with an E. Therefore, if this is an electron capture reaction, you're going to only see the representation of an E instead of a beta. Now then, this is a situation where we actually have more than one guy on the left side. So, gnarly, changing things up slightly. Well, the mass number for this particular electron capture reaction involving potassium-40, this is going to be very simple. We have 40 as the mass number for potassium, and our captured electron has a mass number of 0. Therefore, 40 plus 0 gives us a total of 40 for the mass number on the left side. Now the right side has to have the same number as well, and we only have one component. Therefore, we can simply put 40 in for that. Now to sum up our atomic numbers, or technically the atomic number of potassium and the charge number from the electron, that would be 19 plus negative 1, or 19 minus 1, which would be 18. Therefore, our missing component on the product side has to have a atomic number of 18 as well. Going to our periodic table, we see that the element with an atomic number of 18 is going to be another groovy noble gas, which would be argon. So, gnarly. Let's see. Argon. There we go. And boom, that is an electron capture reaction. Now then, we do have other types of nuclear equations. These ones are going to be more or less called bombardment. Not really decay because you're not having a nuclei break apart into stuff. This bombardment reactions can be either multiple nuclei actually colliding with each other, or say a proton colliding with the nucleus, a neutron colliding with the nucleus, that would be neutron bombardment, or essentially we have particles or other nuclei bombarding or colliding with another nuclei. And these could produce a range of stuff. Now, one example of bombardment would be proton bombardment. Now, a proton is simply a hydrogen nucleus. So you could represent it as H with a mass number and atomic number of 1, but to represent this as a particle and not a whole atom, I'm going to use only P to represent a proton. Now, proton bombardment, this is simply a nuclei colliding with a hydrogen nucleus. This is simply a nuclei colliding with a hydrogen nucleus, aka a proton. Now, there can be nuclear bombardment from another nuclei or neutron bombardment from a neutron. They're basically the same thing. We're just replacing what we're hitting our nuclei with. Well, in this case with proton bombardment, here is an example of proton bombardment. And in this case, we have a couple unknowns, but the numbers have already been filled in. So, in this case, we can just go directly to the periodic table. What has an atomic number of 9? Well, that would be fluorine. This guy right here. Now then, the other unknown would be what has an atomic number of 1 but a charge of 0? Well, that would just be a neutron, so lowercase n. Now, typically what I would have had is actually have these guys blank. So just to basically show what's happening. If, say, I give you the identity of this neutron, therefore to add up the mass numbers, simply it would be the oxygen's mass number of 18 plus the proton it was hit with, or 1, 18 plus 1 equals 19. Now then, on the right side of the equation, we need a total of 19. Oh, there we go. We're going to need a total of 19. So what plus 1 gives us 19? Since we have 1 already from the neutron. So what plus 1 equals 19? Well, 18. Therefore, in this case, the mass number of our two nuclei do not change. Now let's go to the atomic number. Well, the atomic number is simply going to be 8 from oxygen and 1 from the proton. Therefore, 8 plus 1 is going to be 9. Now then, for our missing atomic number on the right side, well, neutrons have a charge of 0. And when we're adding up these numbers, we add up the charge as if it was an atomic number. Therefore, what plus 0 gives us 9? Well, 9 itself. And, well, from the periodic table, the element with an atomic number of 9 is fluorine. So, there we go. You saw situations of decay which involved either positrons, electrons, alpha particles, things like that. You also saw an example of bombardment, in this case proton bombardment. So effectively the key for these nuclear equations is simply balancing out the mass numbers, the top left numbers on both sides of the equation, and then also balancing the lower left atomic numbers on both sides of the equation. And then if you know the atomic number of your unknown nuclei, well then you can go to the periodic table and determine its identity. Or if it makes more sense that that is actually a particle and non-nuclei, well then just put in the identity of the particle. For example, if you saw that you had 1 and 0, 1 for the mass number and 0 for the atomic number as the missing component, well then just fill it in with an n. This week's bonus is essentially these 3 equations right here, which you can fill in. Now the top one would be an example of nuclear bombardment, where essentially 2 nuclei, they come and collide together to form another nuclei. Now, for the second equation, you would see nuclear bombardment again between a hydrogen 3 atom or hydrogen 3 nuclei and a helium 4 nuclei, forming one other nuclei and a neutron. And the bottom left example, I'm pretty proud of, is very theoretical. Essentially, some component breaks down into a positron, a fluorine atom, and a neutron. While not really experimentally valid, this is just another example to help get you understanding the addition of mass numbers and the addition of atomic numbers. So, fill in these 3 guys and submit them by the end of next week. And, well, yeah, same rules as always for extra credit. Once again, it is a pleasure to be teaching you guys nuclear chemistry. And without a doubt, at minute 1930, it is a pleasure to be teaching you guys as always.